Welcome to This Explainer. Today, we're tackling what is, hands down, one of the most fascinating and, frankly, complex puzzles in artificial intelligence. It's a challenge known as Word Sense Disambiguation, or WSD for short. At its core, it's about something we humans do effortlessly every single day, understanding the true meaning behind the words we use. But how exactly does a computer parse human nuance, especially when our language is just so endlessly full of quirks, double meanings, and hidden context? Well, it's been an incredible journey from early computing all the way to modern AI, and we're going to unpack exactly how it works.
Okay, let's dive into this. Here's our roadmap. We'll start with the mystery of meaning, look at early dictionary rules, explore how AI learned from data, dive into the neural network revolution, and then finally check out how we measure success and what the future holds.
Section 1. The Mystery of Meaning. Let's look at how ambiguity actually tricks computers. To really grasp the sheer magnitude of this problem, we have to start by looking at human language itself, which is wonderfully, but let's be honest, frustratingly messy. If I just walk up to you right now and ask, "Hey, what does the word bank mean?" your brain immediately starts searching for context. You instinctively know it could mean a few different things. But a computer has absolutely zero intuition. Left entirely to its own devices, it literally just has to guess.
Think about these two phrases, "I deposited money in the bank" versus "he sat on the riverbank." The letters B-A-N-K are exactly identical, but the context completely changes the reality of the sentence, right? If a computational model gets this wrong, it might actually think you're trying to store your life savings in a muddy river. Figuring out the correct meaning of a word in a very specific context, well, that is the exact definition of word sense disambiguation. Now, this ambiguity creates massive headaches for AI, and it usually comes in two different flavors. The first is polysemy. This is when a word has multiple related meanings. Take the word plant. It could be a leafy green living organism in your garden, or it could be an industrial facility manufacturing cars. They are related concepts, something established or rooted in a physical place, but practically speaking, they are very different. Because the meanings are so closely related, it creates this super tricky gray area for machines trying to pinpoint the exact context.
Contrast that with homonymy. This is when words have entirely unrelated meanings, but just happen to share the exact same spelling. Think of the bark of an oak tree versus the bark of a golden retriever. When you only have really sparse contextual clues, like say in a super short text message, resolving this kind of ambiguity becomes incredibly difficult for a machine. It's a massive hurdle in computational linguistics.
Section 2. Early dictionary rules. This is all about knowledge-based WSD.
So, how did early computer scientists actually try to solve this? Well, back in the 1980s, AI relied heavily on structured logic and really strict rules. One of the earliest breakthroughs was the Lesk algorithm, which Michael Lesk proposed back in 1986. Think of this algorithm kind of like a detective armed with nothing but a dictionary. First, the algorithm grabs the dictionary definitions for all possible meanings of the ambiguous word. Then, it compares those definitions with the definitions of the other words in the sentence. Finally, it simply counts the overlapping words and picks the maximum overlap. So, if the sentence is about a river, the definition of the water edge bank is going to share way more words with the surrounding sentence than the financial definition ever will. It's a highly logical, rule-based approach.
But counting exact word overlaps definitely had its limits, which naturally pushed the field toward semantic similarity measures. And this brilliantly illustrates how that works. Look at the sentence, "The crane lifted the heavy load." By using resources like WordNet, which basically maps out how words relate to each other, semantic similarity measures can mathematically link the words lifted and load directly to the machinery definition of crane. By measuring that semantic distance between the words, the system completely rules out the interpretation of a long-legged bird. Section 3. Learning from data. We're getting into supervised and unsupervised methods. By the time the machine learning era rolled around, researchers realized that language just evolves way too fast for rigid dictionaries. So they started feeding algorithms massive amounts of real-world text data. They did this via two primary pillars. The first is supervised learning. This is kind of like a student practicing with flashcards. It requires massive amounts of human-labeled training data, where the correct sense of a word is explicitly pointed out. The second pillar is unsupervised learning. Here, the machine is basically left alone to group words by context without any labels, finding natural clusters or patterns entirely on its own.
In supervised WSD, traditional classifiers, like support vector machines and decision trees, act like eager students conducting an active investigation for context. They look at neighboring words. They analyze part-of-speech tags, like is it a noun or a verb. They look for collocations, which are just words that frequently pop up together. And they study syntactic dependencies, breaking down those subject-object relationships. It's a highly analytical way of turning a sentence into mathematical features just to guess the correct meaning.
Section 4. The Neural Network Revolution. The Era of Deep Learning and Transformers. Now, prepare for a monumental shift in scale. The strict rules and manual feature extraction of the past were completely blown out of the water by the leap from static to dynamic understanding. Early neural networks used static word embeddings, like word to vec. These mapped words to fixed mathematical spaces based on co-occurrence, but polysemy still tricked them, because a word always got the exact same static representation. Now, what's really interesting about this slide is the shift to contextualized embeddings, like BERT. BERT acts like a mind reader, feeling the room. The vector it assigns to a word dynamically changes based on the surrounding context of the specific sentence. Let's actually apply this to the exact problem we started the explainer with. As the source material notes, in the sentence, "He sat by the bank," BERT produces a mathematical embedding for bank that is instantly and contextually aligned with river rather than financial institution. It doesn't just look up a static dictionary entry. It dynamically adjusts the definition based on the entire sentence structure in real time. It truly is a stunning technological achievement that solves the very mystery we set out to understand.
Section 5. Measuring Success and Impact. How do we actually grade AI? With all these incredibly fast-evolving models, from Lesk algorithms to BERT, how do developers actually know if these systems are improving over time? I mean, how do you give an AI a report card? Well, they use a strict mathematical grading rubric, evaluated against a human-verified gold standard. Precision measures accuracy. Out of all the senses the AI guessed, how many were actually right? Recall measures completeness. Out of all the words it was supposed to disambiguate, how many did it successfully catch? And the F1 score just combines both into a single harmonic mean. Benchmarks like sense value use these exact metrics to pit WSD systems against each other on a global scale.
So, the crucial point is, why does this all matter outside of a computer science lab? Well, you actually rely on Word Sense Disambiguation daily. When a search engine accurately interprets your query, that's information retrieval powered by WSD. When software flawlessly translates a polysemous word into another language, or when an algorithm gauges the sentiment of thousands of customer reviews without getting tripped up by double meanings, that is WSD actively making our digital world function. It's literally foundational to how we interact with technology today.
Section 6. The Future of Understanding. Let's look at the road ahead. We've journeyed from rigid dictionary rules to dynamic neural networks that can practically read the room. But the evolution of how machines learn meaning is definitely far from over. Despite the incredible power of modern large language models, AI still stumbles. When you train a model on medical texts, it often totally fails when reading legal documents. That's called a domain adaptation failure. AI still struggles with incredibly subtle, fine-grained sense distinctions that humans just grasp intuitively. And for a lot of languages around the world, we simply don't have enough annotated text data, the resource limitations, to properly train these massive architectures. Which brings us to the end of our explainer and leaves us to ponder the ultimate boundary between computational pattern recognition and genuine comprehension. With all these staggering advances, will AI ever truly grasp the subtle, lived nuances of human language? Or is meaning, at its core, ultimately a human monopoly. Thanks so much for exploring this fascinating topic with me. Keep wondering and keep learning.